Hello everyone, this is Namita.
And this is Nazia.
Today we're going to talk about the experiment, verification of inverse square law for beta rays. So let's get started. The aim of the experiment is to prove that the intensity of beta rays falls inversely as the square of the distance. What exactly is inverse square law? Let's have a look at it. Inverse square law states that the radiation intensity is inversely proportional to the square of the distance. For better understanding, please have a look at the picture. Here, S is the source and R is the distance of the source from the detector. We can see that as the distance doubles, the area quadruples and thus the initial radiation amount is spread over the entire area and is therefore reduced proportionately. In other words, the same number of particles passing through an increasing area means that particles per square meter decreases with the distance. The apparatus required are GM counter, beta radiation source, GM tube holder and the source holder.
Let us see what is a Geiger-Muller counter. Geiger and Muller developed a particle detector for measuring ionizing radiation in 1928 and they named it as Geiger-Muller counter. Ionizing radiation include alpha particles, beta particles and gamma rays. A GM counter can count individual particles at rates up to about 10,000 per second and they are widely used in medicine and in prospecting for radioactive ores. This is the picture of GM counter which we will be using in our experiment. Let us quickly see the construction of a GM counter. A GM counter consists of a hollow metal case enclosed in a thin glass tube. This hollow metal case acts as a cathode. A fine tungsten wire is stretched along the axis of the tube and is insulated by ebonite plugs. This fine tungsten wire acts as anode. The tube is evacuated and then it's partially filled with 90% argon and 10% ethyl alcohol. The fine tungsten wire is connected to positive terminal of a high tension battery through a resistance R and the negative terminal is connected to the metal tube. The direct current voltage is kept slightly less than that which will cause a discharge between the electrodes. At one end of the tube, a thin window of mica is arranged to allow the entry of radiation into the tube. Now, if 400 volts is applied to the thin wire in the middle and if particles are allowed to come into the tube, these particles take an electron from argon atom. The electron is attracted to the central wire and as it rushes towards the wire, the electron will knock other electrons from argon atoms. This causes an avalanche. Thus, one single incoming particle will cause many electrons to arrive at the wire, creating a pulse which can be amplified and counted. Let us in detail understand the principle of the GM counter. When an ionizing particle passes through the gas in an ionizing chamber, it produces a few ions. If the applied potential difference is very strong, these ions will produce a secondary ion avalanche whose total effect will be proportional to the energy associated with the primary ionizing event. If the applied potential difference is very high, the secondary ionization phenomena becomes so dominant that the primary ionizing event loses its importance. In other words, the size of the final pulse produced depends only on the triggering off of ionization by an ionizing particle, but it is independent of the energy of this particle. A high energy particle entering through the mica window will cause one or more of the argon atoms to ionize. The electrons and ions of argon thus produced cause other argon atoms to ionize in a cascade effect. The result of this one event is a sudden massive electrical discharge that causes a current pulse. The current through R produces a voltage pulse of the order of 10 microvolts. An electron pulse amplifier accepts that small pulse voltage and then it amplifies to about 5 to 50 volts. The amplified output is then applied to a counter. As each incoming particle produces a pulse, the number of incoming particles can be counted. Now, there is a threshold voltage below which the tube doesn't work. This can be several hundred volts. After this, the number of pulses is proportional to the voltage. This region is known as proportional region. If the applied voltage is increased further, then a point will be reached after which the count rate remains constant over a certain region. This region is known as plateau region or Geiger region, and this region is used for our Geiger-Muller operation. Now, beyond the plateau region, the applied electric field is so high that a continuous discharge takes place in the tube and the count rate increases very rapidly. It does not require any ionization event to happen, so that the tube must not be used in this region. Some of the precautionary measures while operating a GM counter are: the operating voltage must correspond to the midpoint of flat plateau region of the plateau graph. If the continuous discharge is produced, the voltage should be lowered. The applied voltage must be relatively stabilized, and introduction of light should be prevented to avoid photoelectric effect. In our experiment, we will be using beta source. So let us study about beta particles and beta source. Beta particles are high energy, high speed electrons or positrons that are ejected from the nucleus by some radionuclides during the radioactive decay, which we call it as beta decay. Beta decay normally occurs in a nucleus that has too many neutrons, and it occurs to achieve stability. If some properties of beta particles are there, they are: beta particles have mass which is half of 1,000 of the mass of a proton. They either carry a single negative electron or a positron, that is a single negative charge or a positive charge. Beta particles have very small mass and they can be released with high energy. They can reach relativistic speeds, that is close to the speed of light. Beta particles are very less ionizing than alpha particles, and they generally do very less damage for a given amount of energy deposition. They typically have ranges of tens of centimeters in air, that is they are energy dependent, and a few millimeters in materials. So we saw about beta particles. What is a beta source? Beta emission occurs when the ratio of neutrons to protons in the nucleus is very high. What happens is an excess neutron transforms into a proton and an electron. The proton stays in the nucleus and the electron is ejected energetically. Many beta emitters occur naturally in the radioisotopes which are found in natural radioactive decay chains of uranium, thorium and actinium. The examples include lead-210, bismuth-214 and thallium-207. You have the reaction of thallium-207 which decays into plumbum-207, that is lead, and one electron. This is the picture of a beta source.
Before starting with the experiment, I'll tell you how to operate this GM counting system. So we'll switch it on. So as soon as we switch it on, this is the visual display which we get over here. This is very easy. We have 6 keys over here, as you can see. This is the start, stop, store, program, and this is the up key and down key, the directions. Here we have a knob which shows the voltage or the operating voltage which we will set for this device. For this, we will keep this at 450 volts. As you can already see, high volts, it's already at 450 volts. It's almost at that. So if we press the program, there will be many functions which we will be able to use in this device. Here you can see the high voltage. When I press this, the timer comes, that is that it says 60 seconds. It's very easy to operate. You can make it 120 seconds, 100 seconds or whatever you want according to the experiment. With the help of these keys, navigation keys, that is this way. As you change, the arrow mark changes on these digits like this. You can make it 65, you can make it back to 60, or you can make it, so it goes, the timer goes in seconds. So this is how you will be using the GM counting system. This is the preset time.
The GM tube holder here is not closed and is exposed to radiations other than beta rays. So to eliminate the error in counts due to other radiations, we take background counts, that is counts when beta source is not placed in the GM counter. So 5 background readings, that is B1, B2, B3, B4 and B5 are taken at 450 volts for 60 seconds each. You can see that the high voltage is set to 450 and the preset time is 60 seconds. And we can start. So once we start, the background readings will be taken. Yes, now we are at 52 seconds. And yes, now we got the readings for 60 seconds. At 60 seconds, we have the count is 15 here. So similarly, we'll take 4 more readings and then we'll calculate the average background count. All the background readings are tabulated as follows. This is the tube holder, and as you can see within it you have different slots. Each slot is 0.5 centimeter apart. So the first reading will be taken at 2 centimeters away from the GM tube. So 2 centimeters away from the GM tube would be the second slot. So at first we'll place the source, that is our beta source, in the second slot. And after placing the source there, we'll set the high voltage to 450 volts and time to 60 seconds. The voltage is set to 450. Once that's done, we can start the count. This will be our first reading. Yes, now we are approaching 60 seconds. Once the time is done, the counts will stop by itself. So here we can see that our count is 482 at 450 volts for 60 seconds. That will be our first reading, 482. So we took readings for 2 centimeters. Now for the second trial, we'll be taking readings at 2.5 centimeters. So that will be the next slot, the slot immediately after the 2 centimeter slot. Here, yes, the third slot. So the source is placed at 2.5 centimeters away from the tube, GM tube, and the time is set to 60 seconds and high voltage is at 450 volts. Once that is done, we can start the counting. Again, similar to the previous reading, we'll have to wait till 60 seconds. Similar to the previous trials, we'll take readings at different distances by changing the slots. So as I said, each slot is 0.5 centimeters apart. Now I'll show the readings for the last slot, that is 7 centimeters away from the GM tube. This slot is the 12th slot in the GM counter tube. So let's get started. Here the voltage is set to 450. The time is set to 60 seconds. And then, yes, we can start the count. So the count at 7 centimeter distance and at 450 volts for 60 seconds is 36.
While explaining the procedure of this experiment, we saw how do we calculate the background readings. We have to tabulate them as shown. That we have to take 5 background readings, B1, B2, B3, B4, B5. So after taking these background readings, we have to take the mean of these background readings or the average background count. The average background count which we have got is 14.4. Now if we calculate the background count rate, that is 14.4 divided by 60 seconds, we get 0.24 counts per second. This is the first table. The second table is as shown, that is the first column has the distance d in centimeter, which is the distance of the slots from the GM tube, which is 2, 2.5, 3, 3.5 up till 7 centimeters. Here the second column shows corrected counts n in 60 seconds. During our experiment, we saw that for this slot that is 2 centimeter away from the GM tube, the count which we got was 482. Now what is corrected counts? This 482 we have to subtract background counts from 482, that is 14.4. So 482 minus 14.4, we get 467.6. This is our corrected counts n in 60 seconds. Similarly, for all the next trials, that is up till 7 centimeter, we have to find the corrected counts. This is the next column. The next column is net count rate R in 1 seconds. So the corrected count was for 60 seconds. To find it for 1 second, we have to divide the corrected count by 60 seconds. 467.6 divided by 60 will give us 7.793. Similarly, you have to find all the net count rate for all the trials over here. The next column is of product of R, that is net count rate, and D square, that is the distance. So if you do the product of R and D square, let us name it as C, you will get few values over here. The next column is 1 by D square, but it is not in centimeter square, but it is in 1 by meter square, inverse of meter square. You have to fill this next column with these values. The next table is of, from the previous table, you have to take distance D and the net count rate R. You have to write them, and then you have to tabulate or calculate log of D and log of R. Similarly, for all the 11 trials, you have to calculate log of the distance and log of the net count rate and tabulate them in this way. So after tabulating, you have 3 sample graphs shown over here. The first graph is of net count rate R versus distance D in centimeter. For this graph, you will get an exponentially decreasing curve. The second graph is net count rate R versus 1 by D square. This graph is a straight line which passes through the origin. The next graph is of log R versus log D. This is a straight line with a negative slope, as you can see. Now, after plotting these graphs, what are our understandings or what are our analysis for this experiment? The sample graphs are also attached over here. Now, I told you there is a column of R into D square in the first table. This R into D square, when you calculate, you will find that these values are almost constant for all the trials. Few fluctuations may be observed, but they are almost constant. If they are almost constant, you can imply that your experiment is correct, and that is inverse square law is obeyed. As I told, the graph net count rate R versus D is an exponentially decreasing curve, as you can see in the sample graph also. Whereas the next graph, that is net count rate R versus 1 by D square, is a straight line which passes through origin. The next graph is a very interesting graph, that is log R versus log D. It is a straight line, and it is a straight line with a negative slope. That is, when you calculate the gradient of this line, you will find that the gradient comes almost around -2. When the gradient is almost around -2, here we have got it as -2.25. You can say that inverse square law is obeyed. So after all your experimentation, all the tabulations and all the plotting of the graphs, and when your analysis is proved correct, you can say all these analyses imply that our inverse square law for beta rays
With this, we come to the
obeyed.
end of the experiment. Let's have a quick recap of everything we saw. In the beginning, we discussed what inverse square law was, and then we discussed what GM counter was, its construction and functioning. And later, we spoke about beta radiation source and its properties. And with all of that, we proceeded with the experiment. We first took background readings, and then we also spoke about why we need background readings. And then we proceeded to take counts with the source, that is beta source. When all of that was done, we did the calculation and we plotted graphs. We had 3 graphs. The first one was net count rate R versus distance D. The second one was net count rate R versus 1 by D square. And the third one was log R versus log D. With the nature of these 3 graphs, we could easily verify inverse square law for beta radiations. With this, we come to the end of the presentation. Thank you.